I am so glad you're here because today we're going to be talking about all the different types of reactions that carboxylic acid derivatives can do. From acid chlorides, anhydrides, esters, and amides, we're going to explore all the different ways that we can transform these functional groups into new ones. And we're going to add these tools to our toolkit when performing multi-step synthesis. And stick around to the end because I have some practice problems that should help for your next exam. First up, let's explore how we actually prepare acid chlorides. So acid chlorides can be made from carboxylic acid by introducing thionyl chloride or phosphorus trichloride to make our new acid chloride functional group and replacing that carboxylic acid. Thionyl chloride contains a sulfur at the center with a double bond to oxygen and two sulfur to chlorine bonds. This makes the sulfur group extremely electrophilic. From here, if we consider the resonance structures that are possible for something like carboxylic acid, remember these electrons can move down to create a new oxygen to carbon double bond, which will allow these pi electrons to attack the electrophilic sulfur atom. From here, this will kick up the electrons between the pi electrons from sulfur to oxygen, allowing us to create our intermediate. This intermediate is going to contain our carbon to oxygen double bond, which still has a hydrogen on it, making this positively charged. Additionally, now we have this oxygen atom attached to the sulfur, which has become a new tetrahedral sulfur with a negatively charged oxygen attached to it, as well as our two other chlorines. From here, these electrons can come back down to sulfur and kick off the good leaving group, chloride, allowing us to generate a free chloride, as well as our other intermediate, which again still has our oxygen double bond that is positively charged, allowing us to place our oxygen here with sulfur here, and our chloride still present. Now remember, this chloride that we have generated as an intermediate can now come in and do things like deprotonate the hydrogen, allowing us to create our neutral species. This generates a new carbonyl compound, which has a fantastic leaving group in that it has now this portion, which can be a very good leaving group to recreate our thionyl chloride. What happens is we get nucleophilic attack by a chloride anion at this carbonyl carbon, kicking up the electrons, allowing us to generate a new carbon tetrahedral species, which is going to have the chloride on it, as well as the rest of the species drawn here. At which point, these pi electrons can come back down and kick off that leaving group, allowing us to finally generate our new acid chloride. And this is the mechanism for using thionyl chloride to turn carboxylic acids into acid chlorides. You'll recall from our previous video about carboxylic acid derivatives that acid chlorides are going to be the most reactive carboxylic acid derivative. In fact, they can be turned into all of the other carboxylic acid derivatives. So we just learned about how to turn a carboxylic acid into an acid chloride using thionyl chloride, and we can actually turn the acid chloride into a carboxylic acid simply by the addition of water. We can also turn acid chlorides into esters through the addition of an alcohol, so ROH, where the R is any alcohol, could be ethanol, methanol, etc., and pyridine. So pyridine is often the solvent used in this process, and we add an alcohol to create a brand new ester. We can turn acid chlorides into amides. So an amide is, remember, is going to be your carbonyl that contains a nitrogen containing group on the other carbon, on the other side of the carbon, just by adding excess amounts of an amine. So ammonia, for example, an excess amount meaning XS. Ammonia would allow us to create a primary amide, but we could also do something like create, by using excess secondary amines, to create a brand new tertiary amide. So this is a way that we could add different types of R groups to our amide. We can also use acid chlorides to create ketones. So remember, a ketone is going to be an R group coming off the carbonyl by using an organometallic reagent, which we'll learn about more in this course. So R2 Cooper lithium, that's called a Gilman reagent. Acid chlorides also undergo reactions with Grignard reagents. So RMgBr, for example, is what's called a Grignard reagent. And when you also have an acid in your system, so H3O plus just meant to depict any sort of acid, we can actually create a brand new alcohol species that contains two different R groups. So we can create brand new tetrahedral carbons with an alcohol on them by adding an excess amount of these Grignard reagents in the presence of acid. We can create primary alcohols by using lithium aluminum hydride, which will allow us to create a primary alcohol where the other R groups would just be hydrogen atoms. And then finally, we can also create aldehydes. So remember, an aldehyde is going to be that carbonyl with a hydrogen coming off the carbon by using this reagent. So lithium aluminum OR3 in the presence of an acid. And these are all the different transformations that are possible by using acid chlorides. We can go to carboxylic acids, esters, amides, alcohols, etc. And it'll be important to keep all of these in mind when doing multi-step synthesis. Acid chlorides can also be useful for creating anhydrides. By deprotonating a carboxylic acid, it will undergo nucleophilic acyl substitution to create a good leaving group, where now we have created a situation where the pi electrons can come back down, kick off the chloride, and leave behind our anhydride. Additionally, one last way that you can make anhydrides is actually just going to be using anhydrous carboxylic acids under incredibly high temperatures. So the temperature would be incredibly high, like 900 degrees Celsius, and it will undergo a homocoupling, allowing us to generate brand new anhydrides. Like acid chlorides, anhydrides can be converted back to carboxylic acids simply with the presence of H2O or water. Again, like acid chlorides, anhydrides can be converted into esters through the addition of an alcohol. So an ester can be created through the addition of an alcohol. Again, like acid chlorides, we can create primary amides simply by adding different amines to create brand new amide bonds. So a primary amine could be formed through the addition of excess ammonia, or if we wanted to make a secondary or tertiary amide, we would simply add different types of amines to our system. So excess amines can be used to create brand new amides from anhydrides. Again, like acid chlorides, we can actually create ketones by simply adding that Gilman reagent, which again was R2 copper lithium, can be added to anhydrides to make ketones. Alcohols can be made by adding excess amounts of Grignard reagents. So again, that's some R group with magnesium bromide, for example, and some acid, H3O+, we can create brand new alcohols as well. And we can create ones that have a stereocenter potentially because we're creating tetrahedral alcohols. Just like acid chlorides, we can also make primary alcohols by using something like excess lithium aluminum hydride as well as water or acid to create that primary alcohol. So remember, a primary alcohol is going to be attached to a carbon with two other hydrogen atoms attached to it. And again, like acid chlorides, we can use lithium aluminum ethers in order to create brand new aldehydes. So this allows us to create aldehydes, which again is carbon to hydrogen with the carbonyl functional group. So hopefully you're noticing a trend here where all of these different carboxylic acid derivatives undergo very similar transformations in order to create these different functional groups. One of the simplest ways to make esters is going to be through deprotonation of a carboxylic acid followed by an SN2 or substitution reaction to create a brand new ester bond. A more common way that people make esters, though, is called Fischer esterification, where you use an alcohol and some catalytic acid, and you can convert carboxylic acids very readily into brand new esters. And again, this is called Fischer esterification. So Fischer esterification is the most common way that these types of esters are made in industry. The mechanism for Fischer esterification follows a pathway that you might predict, where the catalytic amount of acid is allowed to protonate that carbonyl oxygen to create a brand new positively charged species, which will allow for this carbonyl carbon to be attacked by things like our alcohol. So once we have made this more electrophilic, the lone pair on an oxygen from alcohol will come up, kick up those electrons to allow us to create a brand new tetrahedral alcohol. and allow us to further undergo the transformation to an ester through a series of proton transfers. So remember, we still have plenty of our alcohol present, which has lone pairs on the oxygen, which will deprotonate that OH group, allowing us to create a neutral species. So now we have a fully neutral compound where we have two alcohols and an OR group. From here, one of the alcohols can be protonated by the brand new acid that has been formed, allowing us to create a good leaving group, which is going to be an OH2 derivative. So we have our alcohol, we also have a brand new OH2 that is positively charged, and our OR group. From here, the electrons can come down from one of the oxygen atoms and kick off that good leaving group, allowing us to create a brand new protonated ester, where now this proton that is on the carbonyl oxygen can subsequently be deprotonated by, for example, the alcohol that is still present in our compound, allowing us to finally generate our brand new ester. Nitriles are commonly made through substitution reactions with alkyl halides. For example, an alkyl bromide will undergo a substitution reaction with sodium cyanide to create our brand new nitrile. Additionally, nitriles can be made from amide bonds. So remember, an amide is going to be a carbonyl compound that contains a nitrogen-containing group on the carbonyl carbon by adding, again, that thionyl chloride that we've learned about in the preparation of acid chlorides in order to create our brand new nitrile. And the byproducts of this are going to be that sodium dioxide and hydrochloric acid. Now, nitriles and amides are unique in that they really only undergo two different types of reactions. So they are the least reactive of the carboxylic acid derivatives, and therefore they typically only create one other type of functional group transformation, and that is going to be the creation of a primary amine. So a primary amine can be created from both of these. From nitriles, we just add lithium aluminum hydride in the presence of water to create our primary amine. And we use the exact same reagent, and actually the lithium aluminum hydride can reduce this carbonyl oxygen to again create that primary amine. Now let's try some practice problems to gauge your understanding. Pause the video to try these problems independently, then resume the video to check your answers. For the first problem in this video, we learned that thionyl chloride is a method used to convert carboxylic acids into acid chlorides. So for that reason, the product of this transformation is going to be a new acid chloride. For the addition of lithium aluminum hydride to esters, basically what you can think of lithium aluminum hydride as is a source of a hydride species or a hydride anion. So at this position, I see that there's an oxygen, and I also see at this position that there's another oxygen. When doing so, what's actually happening is, remember, this is a H-, which is a nucleophile. So what would actually happen, and we'll learn more about this later in the semester when we talk about organometallic reagents, but that hydride source actually attacks at that carbonyl carbon. Following nucleophilic acyl substitution, this will actually eventually kick off this part right here where we have our ester bond, which means we'll get a splitting of this bond in order to create our brand new product, which, as you'll see in a moment, is going to be a dialcohol or a diol. And since we have our acid, I know that this is going to create alcohols because we're going to end up protonating any sort of O- group that we create in this transformation. So even though we haven't learned about the mechanism yet, I can still see that all of these oxygens will eventually be protonated. So if I were to split this compound at this location, at this bond, that leaves behind, I still have this species. I see that I have one carbon that has an alcohol attached to it because I have one carbon separating this species with the dimethyl groups from the oxygen. And then I see on the other side I have 2 carbons separating the oxygen. So 2 carbons followed by an alcohol. So for that reason, this would be the product of this transformation with lithium aluminum hydride into a cyclic ester. Remember that Fischer esterification is a way to turn carboxylic acids into esters by using an alcohol. So if you have an alcohol source and a carboxylic acid, you can create a brand new ester. So we're looking for the different species that will allow us to create the ester that we were given in the problem. That ester looks like this, and you were given this in the problem, where you have the isopropyl ester as well as your ethyl group on this side. So from here I see that the bond that has been formed is between the carbonyl carbon and this single bond to the oxygen, which means that our carboxylic acid part is going to contain that ethyl group coming off of it, and the alcohol that we use is actually just isopropanol. So this would be the two different species that would come together to form the ester that we were giving in the problem. Organic chemistry too is a lot about learning new reactions in order to utilize them in multi-step synthesis. This problem is an example of that. In order to convert an alkyl bromide into a carboxylic acid, we need to consider the different types of reactions that we've learned. The first step in this reaction is going to be a substitution reaction where you are converting an alkyl bromide into a nitrile. So when we add sodium cyanide to this compound, we actually get a brand new nitrile compound. And we should have been able to recognize this because I see that in this initial one, besides the phenyl group, we have 1, 2, 3 carbons. However, in the product, I have 1, 2, 3, 4. And the formation of this nitrile is one of the only tools that we've learned about in order to add carbons to our species. So in order to get that 1, 2, 3, 4th carbon, I need to be able to do a transformation that will allow me to extend the carbon chain. From here, we can convert nitriles into carboxylic acids through the addition of a strong acid. So when we add the acid, this will serve in order to create our brand new carboxylic acid, which has our extra carbon as opposed to 3. Now we have 1, 2, 3, 4, and this is the overall transformation. So this would be options 1 and 3 combined to create our carboxylic acid from our alkyl bromide. When performing multi-step synthesis, it's often useful to use retrosynthetic analysis. So we were told that this is the product we're trying to form, and our starting material needs to be benzene. So remember, benzene is just this phenyl group with no other substituents attached to it. From here, it's often most useful to just think about the very last step. So work from the back all the way to the front. So one of the things that I see is that the first thing that I need to do is to redraw my compound and identify what functional groups are present. So I see that I have an alcohol at one position and I have an amide at another position. In this video, we learned about creating amides through using carboxylic acid derivatives. One of those methods is actually through the addition of an anhydride. So for example, acetic anhydride will allow us to transform an anhydride into an amide. And the way that we do this is just by adding an amine, which means that if my other reagent was the benzene ring that already has the alcohol on it, and just something like NH3, that these two reagents combined allow us to create this final piece, this amide bond. So this is going to be the very last step. Previously, we learned about how we create benzene derivatives that contain ammonia on them. So sorry, this should be an NH2. The way that we do that is actually by using something like zinc and hydrochloric acid. That allows us to transform nitro groups into primary amines. So remember, a nitro group can be converted to a primary amine by using zinc and hydrochloric acid. From here, we can use what we learned about different benzene derivatives and those types of reactions in order to transform this molecule all the way back to benzene. From here, I recall that earlier in the semester, we learned about different ways to transform benzene. One of those reactions is through adding sodium hydroxide and an acid. I could convert chlorophenyl substituents into alcohols. So this means that my nitro group must have already been there, and I now have a chloro group, and by working in this direction, I know that if I added that sodium hydroxide and acid, I would turn the chloro into an alcohol. From here, I recall that I could do nitration through the addition of nitric acid and sulfuric acid, and that is actually the method we use to install that nitro group, which means that the preceding reactant must have been just that chloro substituent, so chlorobenzene. And the way that we add chloro to benzene is through a Friedel-Crafts addition, so Cl2 in the presence of FeCl3 is actually how we add chloro groups to benzene. So from here, I have worked all the way from my product to benzene in the backwards or retrosynthetic way. Now we need to turn this into a method to do it in the forward direction. So step 1 would be this Friedel-Crafts addition of chloro. Step 2 would be the nitration of this chloro substituent, which again would add ortho and para, with para being the predominant product or the major product that's formed. Additionally, I recall that step 3 is going to be transforming a chlorobenzene into an alcohol. That means that step 4 is going to be reducing the nitro group to a primary amine. And then finally, the reaction we learned about in today's video is how we turn anhydrides into amides. As you can see, we're really starting to build up our toolkit when thinking about multi-step synthesis. So if you enjoyed today's video, make sure to subscribe to my channel to learn about the other ways that we can transform molecules from one to another. Additionally, leave a comment down below if you have any questions and I'd be happy to help you out. I'll see you in the next video.